Okay guys, so this is the second half of Born-Haber cycles. This is the slightly more tricky ones. So please don't watch this until you've seen my first video, which explains how to do it simply. Because a lot of the things I'm going to do now, you won't get until you've seen that first video. Okay? So from the first video, we know we need to start off with something called our datum line, which is basically our elements in their standard states. So if I'm trying to make Na2O, I need two sodiums and half O2 because I've got one oxygen, so to balance it out I need half O2, that's one oxygen. What I can do is I can form these into an ionic lattice, and my enthalpy change will be my enthalpy change of formation, and my ionic lattice is Na2O, and that will be a solid. And that's lower in enthalpy because I'm forming bonds. That gives energy out. What I can also do is I can atomize, so change into a gas, my sodium. Doesn't really matter which one you do first, you can do sodium or oxygen, as long as you do both of them by the end. So I'm changing 2 moles of sodium solid into 2 moles of sodium gas, and I've still got my half O2 just sitting around having a pie. I can then atomize my oxygen, so that is a gas too. So my half O2 just goes into O, and I've still got my 2 sodium gases there. So make a quick note now. The definition for the enthalpy change of atomization is the enthalpy change associated when we change 1 mole of element in its standard state into a gas. Now we don't have 1 mole of sodium here, we have 2 moles. So whatever this value is, and I've written the values down there, I'm going to need to multiply it by 2. Because I'm not getting 1 mole, I'm getting 2. If I had 3 moles of sodium, I need to multiply it by 3, and so on. Just like in my last video, I then need to ionize my metal, and again, sodium only gets a 1+ charge. If this was magnesium, I'd need to ionize it twice, aluminium 3 times, and so on. So I'm going to ionize this into 2Na+, which is a gas, plus my O, and then I'm going to get 2 electrons given off, because each sodium releases an electron, and there's 2 sodiums, so 2 electrons. This is my enthalpy change of ionization. And just like down here, enthalpy change of ionization is enthalpy associated when we make 1 mole of positive ions. Now, when we're making 1 mole, we're making 2 moles, so whatever this number is, I'm going to need to multiply it by 2. Okay? So you do need to take into account your molar ratios here. What I'm then going to do is add an electron to oxygen, so that is the first electron affinity, Ea1, and that will give me my 2Na+, which is a gas, plus O- gas, plus my remaining electron. And your first electron affinity, if you remember from the last video, is always negative because your negative electron is being attracted to your positive nucleus, gives energy out as it gets closer. But, and this is different to the last video, oxygen needs to gain 2 electrons to become a lattice. So I need to add a second electron. I've already added an electron here, so this already has a negative charge. My electron has also a negative charge. I'm trying to bring 2 like charges together. And as you probably know since year 8, like charges repel, so in order to force them together, in order to force the electron into the oxygen ion, I'm going to need to put in energy, so it's got enough energy to do that. So if I'm adding energy to this, my enthalpy diagram will get higher, because remember, the higher up the board we go, the higher the enthalpy is, or the energy you can think of it. So that will give me 2Na+ gas plus O2- gas, and that is my final ionized gaseous ions. I can then change these into my ionic lattice. Let me just write my second electron affinity there. Ea1 for the first electron affinity, Ea2 for the second electron. And this final line, going back to my lattice, is my lattice enthalpy, which I want to find out. Now, I don't know my lattice enthalpy. Look, here's all my data. Nope, I've not been told it, so I need to figure it out. And I'm going to use Hess's law. So it doesn't matter which route I take, if I start from the same place and I end in the same place, I will end up with the same answer. So I'm going to start from the top and go to the bottom. That's one possible route. Or I can start from the top, go down here, back up, and all the way down here. So what I'm going to do is I'm going to be going backwards pretty much all the way up to my enthalpy of formation. So just like on the last video, I need to take all my numbers, but if I'm travelling against the direction of the arrow, I need to flip the sign on the number. So I'm going to need to rub this off to make space in a second. So I'm going to flip the sign on both my electron affinities, flip the sign on my ionization, flip the sign on my atomizations, but keep the same sign on my formation. And let's not forget, and everybody always forgets this, so please don't, I need to double my atomization for sodium, and I need to double my ionization for sodium, because I have 2 moles of sodium, not just 1. So, let's have a bit of room to work with. My lattice enthalpy is going to equal, flip the sign on both my electron affinities, so minus 790 plus 141, flip the sign on my ionization, and don't forget I need to times that by 2, so that's going to be minus 2 times 496, flip the sign on my atomization of oxygen, so that's minus 249, and flip the sign on the other one, don't forget that's sodium, so we need to times that by 2, so that's minus 2 times 108, and I needed to keep the same sign on my enthalpy change of formation, so that's minus 414. So I'll just do a quick little bit of arithmetic, carry the 2, yep, so that's minus 2,520, don't forget the units is kilojoules, small k, capital J, per mole, minus 1, and that is your answer. Few things just to point out there. Don't forget, if you have magnesium or calcium, something which gets a 2+ charge, you're going to need to ionize it twice. If you've got oxygen or sulfur, anything with a 2- charge, you need to do 2 electron affinities. The first is always negative, the second is always positive, okay, because you're overcoming those 2 negative charges. And don't forget, please don't forget, if you've got 2 or more moles, you need to take that into account by multiplying your numbers by 2 or whatever. Okay guys, so we've noticed this is quite a large, or I should say this is a very negative electron affinity, lattice enthalpy, whereas my answer on my last video wasn't quite so large. So let's talk about what makes the difference between these lattice enthalpies. How do I know whether it's going to be a large or a small one? Well, there's 2 reasons, and what I'm going to do is ask you a series of questions to kind of lead you through the answers to that. So my first question is, when I form an ionic lattice, what causes them to bond together? What type of force is it that holds my positive and my negative ions? Okay, have a think about that. You should have thought electrostatic forces between the positive and negative ions. Okay? My next question, if I have a larger charge on my ions, what will that do to the size of those electrostatic forces? Will it make them stronger or weaker, larger or smaller? Okay, bigger charge. Bigger charge will give a stronger force. Now, we said earlier in my last video that when a bond is made, it gives out energy. And it turns out the stronger the bond, the more energy it gives out. So if I have a larger charge, I have a stronger bond, therefore it will give more energy out. So my lattice, my ionic lattice, will be a lot lower in energy. And that makes my lattice enthalpy more negative. So the first rule is, the larger the charge, the more negative the lattice enthalpy. Now, what a lot of people say here is the larger the charge, the greater the lattice enthalpy. And that can be a bit misleading to write that in an exam. Because if something's greater, that means it's more positive, doesn't it? But lattice enthalpies aren't positive, they're negative. And the larger the charge, the more negative it is. So that's not really greater, that's less, isn't it, if it's more negative. So you should always say the larger the charge, the more negative the lattice enthalpy. But there's another reason as well, and that's to do with the size of the ions. And a little point here, we need to be talking about ions here, not atoms. I might have mentioned atoms earlier. If I have, that was a mistake. Always ions. So don't say chlorine, fluorine and iodine, it's chloride, fluoride, iodide. If you don't say that, if you mess that up, you lose a mark every time. Okay? So size. A few more questions. If I have two large atoms, what we've done wrong there, said atoms, it used to be ions, and I bring those together, for example, I've got sodium and chlorine, chloride, it's not chlorine, it's chloride. So if I bring those two together and they're large, then are they going to be able to pack closer together or not as close together? Okay, so have a think about that. Okay, they're going to be able to pack not as close together. And okay, chlorine and sodium are actually quite small, but compared to, for example, sodium and fluorine, they're even smaller still. So sodium and fluorine can pack closer together than sodium and chlorine can, because chlorine is larger. Now, next question. If they can't pack as close together, is that going to make their forces, so their bonds, stronger or weaker? Okay, think about magnets. If I have two magnets this far apart, do they have a stronger force, or are they going to have a stronger force when they're this far apart? Okay, obviously the closer they get, the stronger the force, therefore the stronger the bond. So what it turns out is if I have two small ions, what's going to happen is they're going to be able to pack closely together, they're going to have a stronger force, a stronger bond, they're going to give more energy out, and that's going to make my lattice enthalpy more negative. Okay, so the smaller the atoms, yeah, again, it's easy to make, it's a really easy mistake. That would lose me a mark. The smaller the ions, the more negative the lattice enthalpy. So if I had two very, very small, highly charged ions, for example, aluminium fluoride, AlF3, that would have an incredibly negative lattice enthalpy because they're small and highly charged. If I had two very large ions, for example, and with only 1 plus charge, for example, I don't know, francium and iodine. Again, did you notice a mistake? It's not iodine, it's iodide. Dead easy to make, but it will mess you up. Because they're very large and they don't have much of a charge, they would have a less negative lattice enthalpy. It would be a very small number. Okay? And that is Born-Haber cycles and lattice enthalpy.